REopt is a techno-economic energy optimization model, offering multi-technology integration and optimization capabilities to help building owners, campuses, and communities meet their cost savings and energy performance goals. This demonstration describes the desktop REopt model, which is used by NREL analysts to provide decision support to NREL clients. Imagine a client asks us to evaluate renewable energy opportunities at one of their sites. All the information about the site can be entered on the REopt Inputs tab. We'll start with the site's location, which will be used to pull renewable energy resource and utility information about the site. Next, we'll enter the amount of space the site has available for renewable energy development. Then, in the top middle section, we'll enter the site's current annual utility energy consumption and annual energy cost, which is used to calculate a blended rate for the analysis. All of the data can be entered here on this tab, or can be pre-populated in a site data file where all inputs to the analysis are saved. Now we will load the site data file, and the rest of this information will be populated from that file. In the Load Profile section, you'll see that for this site we are shaping the load profile based on the Department of Energy Commercial Reference Building Model for this climate zone and building type. On the top right, you'll see the economic metrics we're using for this analysis, including analysis period, discount rates, and energy escalation rates. We can tailor the level of analysis we do based on the level of data available and the goals of the site. By checking this box, we can enter the site's complex utility rate tariff, which includes energy and demand components across different time of day and seasonal periods. We can also upload the site's actual interval data instead of using a simulated load. After we've entered the site's data, we'll look at the technology characteristics. You'll see there is a tab for each technology, and each one contains similar data. On the PV tab, for example, we have installation and operating costs, incentives, and system characteristics, such as minimum and maximum size. We have these populated with defaults, but any of these entries can be changed by the user. Similar information can be updated and verified for each technology. Now that we have entered the inputs and verified the technology characteristics, we'll go to the Dashboard tab to run the analysis. This site is interested in identifying renewable energy technologies that will reduce their cost of energy compared to what they're paying their utility. Therefore, we'll set the optimization objective to min LCC, which means we will minimize the life cycle cost of energy over the analysis period. We set the resolution of the analysis here. When we click Optimize, the model is going to consider all the renewable energy technologies and pick the size of the technology that minimizes the life cycle cost of energy. You can see now that the sizes of the technologies are being returned from the optimization model. Here we can see that 6 megawatts of PV and 15 megawatts of wind are recommended. In this section, we see the associated metrics, including capital costs, operation and maintenance costs, land required, electricity generated, and levelized cost of energy. Net present value is the ultimate decision variable. The model is looking to minimize the life cycle cost of energy, or maximize the net present value, which is the difference between the base case life cycle cost and the renewable case life cycle cost. We can look at how these technologies are being used to meet the load. The load is at the black line at the top, the grid is shown in blue, wind is shown in red, and PV is shown in orange. Together, these three resources meet the load in every time step. After reviewing the initial recommendations, the site decides wind turbines are infeasible due to a nearby airport. So we take wind out of the technology option mix by setting the maximum wind size to 0 on the wind tab, and then rerun. Now we see that when wind is taken out of the consideration, only PV shows up, but at a larger size. Now the client would like to explore opportunities for battery storage. To consider storage in the analysis, we'll go to the Battery tab and turn storage on by inputting a non-zero maximum size. Then we will go to the dashboard and click Optimize. Storage is now part of the minimum cost solution, along with PV. Let's compare the scenarios we just ran. We started with the base case, which is the business as usual or do nothing case, where the site continues to purchase electricity from the grid. You can see that if they continue to purchase all their electricity from the utility, their life cycle cost of energy will be $182 million. If they implement a PV and wind project, their life cycle cost goes down to $166 million, and the net present value is $16 million. However, that wind project is not going to be feasible with the nearby airport. So if we take that out, we'll see that the model recommends PV only, now in a larger size. The PV only solution has a lower net present value than the PV plus wind solution, but still offers savings compared to the base case. Finally, compared to the PV only solution, the PV plus storage solution offers a higher net present value and also enables more PV, because the technologies are synergistic and together more effective at peak demand shaving. Let's look at the dispatch strategy to see what the PV plus storage system is doing. This plot shows 1 week. The load is in black, and it must be met in each hour by either energy purchased from the grid, PV, or storage. While PV generates according to when the resource is available, with storage, you need to decide when to operate it. In every time period, there's a decision to be made about whether to charge, discharge, or do nothing with the battery. And if you charge or discharge, you need to decide how much. Using an economic optimization model allows you to identify the size of storage and associated dispatch strategy that maximizes the economic benefit of the integrated system. You can see that early in the day, PV can shave the peak on its own, but later in the day, PV and battery are working together to reduce peak demand. The peak demand period is too long for the battery on its own, but by using PV to shave much of it and adding in battery on the shoulders, together they are very effective in reducing demand. At this site, demand charges are very different throughout the day. You can see that the peak is shaved to different levels in each demand period. We are not setting demand targets. Rather, these levels are determined by the optimization model. This is the crux of the problem and the power of using the optimization model. If you had built a bigger battery, you could have reduced the peak more, but the savings you would have gained from that would not have covered the cost of the larger battery. If you had built a smaller battery, the cost would have been less, but you would have missed out on the savings that were greater than the additional cost of the larger battery. For more information, visit reopt.nrel.gov.